So today I'll be talking about fine-grained small step semantics for interleaving search. So I want to first talk about what interleaving depth first search is. Specifically, I want to contrast it with something maybe you more familiar with, just a pure depth first search, something like Prolog. So we'll walk through a couple examples. So this first one, so the syntax I'm going to be using is going to be independent of any particular concrete syntax. I'll just have these formula-looking things, but you could write this up in whatever logic programming language you have. And so dogs here is a predicate, which we were to query it. First, we would get out the single dog that will recur. So essentially, dogs will give us this infinite stream of dogs. Cats, something similar, just with cats. And finally, we'll combine those two into dogs, cats, which will first call dogs and enumerate an amount of dogs, and then we'll enumerate an amount of cats. And so if you use a depth first search to evaluate this, something like you might see in Prolog, what you'll end up with is just this infinite enumeration of dogs. And this is bad, right? Because if you're a cat person, we've ended up starving all the cats, and we'll never actually get to enumerate that branch of the search tree because, well, we diverged down the dogs branch. But if you do something like an interleaving depth first search, something you might see in Minicannon, we'll do just that. We'll interleave between the dogs branch and the cat branch. And so that's an example of interleaving depth first search, saving us from divergence. Now let's consider this program here. So same here, again, it's a predicate, but it's now asserting that its two arguments, x, y, can be made to do the same thing. And then the program we're going to run is just this giant disjunction. You see one nesting here, but we have these calls the same. We have one equation in here. And under depth first search, what we'll end up with is the answers come out in order you'd expect. It's an order. If you were to just read the program off the right, you could throw dog, cat, fish. So throw cat, dog, fish. But with interleaving, we get these answers out in a very unintuitive order. So first answer we get out fish, it's actually the last one we wrote. And then second answer turtle, it's actually just the first one we wrote. So this interleaving search leads to some unintuitive behavior. And so that's what so it works by suspending and then resuming the evaluation of branches of your search. And so if you treat branches of your search as something you can pause, go do some work elsewhere, come back to it later, that's what it means to do this interleaving. And so what it gives you, though, is a paired search. So it's sort of balancing the efficiency of a depth first search with the completeness of a breadth first search. And so we saw with the dogs example, dogs, cats, that we avoid diverging on some infinite branch. In the same example, we saw that leads to some unintuitive behavior. And so that's why operational semantics for this search would be good. So next, kind of do some thinking about calculi, expressions, and values. So in a calculus, we tend to think of defining the set of expressions. So let's take the lambda calculus, for example. So we have these function abstractions, function applications. Here we have the numbers, and then we define some set of values, and those values are just the expressions which cannot reduce any further. It's a reduction, and this calculus is just taking our expressions and reducing them to some subset of those expressions, which we call the values, that we can't reduce any further. So I want to think about what that looks like for a logic programming language. So what does a calculus look like for logic programming? So we'll say our expressions are these logical formulas. So here's one expression that we saw earlier. And so when you think about what the values would then be, so you might say, oh, it's those answers you gave off order, so like fish, so on. But that's not even a subset of the expression, so that can't be our value. A better, more clever suggestion would be it's like a set of these equations. But again, that's just like enumeration in the list. That's not a logical formula. Again, that's not our values. So what we'll settle on is this approach. So what we have here is a single logical formula, which is important. It's all disjuncted, and it contains these sets of equations. And so one way you might think about visualizing these or looking at them are these tree-like structures. So our nodes here are these disjunction nodes, and our values are something like a linked list of these answer nodes. So these are all implicitly disjuncted. But that's the key idea. So if you take one thing away today, it would be in the calculus logic programming, your values are these normalized search trees. Those search trees are just disjunctions of these sets of equations. So yeah. So first, we'll go over the semantics themselves. So these are the deterministic semantics, and it works by just rewriting these search tree structures. We mechanize the test using PLT redex, and then we use that mechanization to power this tree-based visual stepper to implement as web app, and hopefully we'll have time for a demo. So a bit about reduction semantics. So as we all know, the reduction semantics is a common way to do these structural operational semantics. And so we'll define a set of evaluation contexts, which will choose the next expression we want to reduce. Then we'll have all these rules, which will rewrite those sub-expressions we put it back in, continue. So beginning with the evaluation context. So conceptually, we'll divide our search tree into two parts. So at the top here, we'll say this is the answer stream. So evaluation, again, we're trying to get down to those normalized search trees where we just have these answers. So at the top of our search tree, we'll have all the answers we've accumulated so far. So our first evaluation context, EA, will grab just below those answer streams. So in other words, it's capturing the part of the search tree where work is still occurring. And second, we use ES to go down into the search tree. So we'll follow our disjunctions down, our conjunctions, and we'll choose some subtree, the search tree to evaluate. Finally, E is just a composition of those two. So we'll take the entire tree, go to our computation happening, pick one of those subtrees, reduce it, move on. So for the most part, we'll be using E for a lot of these rules. The exception being sometimes we use EA if we want something to happen just below the answer tree. So last example here. So turtles here, it's like dog cat, except this time, so we're still trying to enumerate just an infinite amount of these animals, but the recursive call comes first here. So kind of orient you with like what these tree rewrites will look like. So like you can think about that program earlier as like this tree here. So here's our disjunction node, evaluations proceeding down the left-hand side, and our node here is the call to turtles. And so what we'll do is we'll expand it, and then we find ourselves in the same situation. So we keep going down the disjunctions, we hit turtles, expand, expand, expand. And so this is that first search, we diverge down this branch. Yeah. But then again, that's what our tree structures will sort of look like. So to avoid this divergence, we need to introduce interleaving. So the way we're going to do that is we're going to have these delay nodes. And so delay essentially represents this tree has been suspended for now. And so the place we'll put them at are these relation invocations. So there's a lot of places you could put your delays at. One way you can think about why you might do it at relation calls is because that's the only spot really where you can generate an infinite search tree. If you don't have any recursion, your tree will be finite. So interleaving doesn't really matter there. Right. So whenever we try to reduce a relation call, we'll do two things. So the first thing we'll do is just maybe substitute the arguments into the body of the relation. And then we'll also add this delay on top of it. So now that tree is delayed. And then finally, or not finally, but this is interleaving right here. So if we have underneath our disjunction delayed tree, we're going to interleave that disjunction. So what we'll do is we'll take the delay, we'll push it up one level. So now it's above the disjunction. So we'll keep moving up the tree, and then we'll swap the order of the search tree. So if you see here, S1 was on the left before, now it's on the right. S2 was on the right before, now it's on the left. And so the evaluation proceeds on the left side of these disjunctions. So the next time we come around to this disjunction, we evaluate S2. So we'll evaluate the tree that wasn't being evaluated before. Pointer died. Maybe take off the screen. Okay, sorry about that. Right, so as we saw, like the delay moved up the tree. So the way we actually get rid of these delays is this example of something happening right below our answer stream. So once it's right below the answer stream, we'll say we'll just release the delay and then keep evaluating the search tree. Right, so here's what that would look like on the same example earlier. So we're looking at the turtles call again, but that's a relation call. So we'll introduce the delay, we'll substitute the body in. And so now we have the disjunction looking at this delayed subtree. So this is where the interleaving will occur. So we'll push the delay up, we'll swap the order of the trees. So now we're evaluating the goal before that we never actually got to. So that will succeed, become an answer. Yeah, so the delay reached the top of the tree. So we'll release it. This thing is now being evaluated. Say that succeeds, gives us an answer, and we'll proceed again. So we solve the relation call, delay it, swap, move the delay up, release the delay, so it's right at the answer stream, and then evaluation continues. So there'll be turtles all the way down again, but this time we actually do get back these answer nodes. Right, so we'll build up this grammar for our search trees incrementally. But so far we've seen disjunction, these delay symbols. So next I want to look at conjunction. So conjunction consists of a search tree in its left-hand position, and then we'll have a goal on the right side. We'll get to goals later, but for now I want to think about what interleaving conjunctions looks like. So the shorter answer is we don't interleave conjunctions, and that's because this goal on the right-hand side is waiting for the thing on the left-hand side, the search tree, to come back with an answer. So we can't really evaluate the goal until that happens, and so we'll just push the delay up through the conjunction. Right, so next we have our goal states. So I won't get into exactly what a state constitutes here, but it's something like the accumulated list of constraints. So you can't evaluate a goal in isolation, you have to evaluate it some state. Some of these are evaluated within the context of those constraints. And so that's where our goal states are. They'll be for our search trees. So our goals, as we've seen before, we have relation calls. Those are where we put the delays on top of. We have unification, so this is first order syntactic equality. We have fresh variable introduction. We have goal versions of our disjunctions and conjunctions. And so interested in how these are evaluated and more about the goals that's in the paper, but we won't really consider that for now. We're only focused on the search behavior. Right. So we'll say a goal can succeed, in which case it will turn into this little green node. And again, it has a state, so it has those constraints that it succeeded in. Or we can say the goal failed, in which case it will go to this empty middle. So yeah, our answer streams consist of what we saw before. It's like a linked list. We have an arbitrary amount of these answers, and then right below the answer stream, we'll have the search tree. Right. So as I said before, we won't get into how these goals are evaluated, but we'll just treat them as these atomic steps. So we'll say the goal can either succeed, in which case we'll go to this green node, or it can fail, in which case it goes to this white node. So now we're going to be working with pushing these answers up the tree. So if we have nested disjunction looking at one of these success nodes, we need to push that up the tree towards the answer stream. And so that's exactly what you see here. We have this thing is nested down here, and we just move it up one level. We'll keep rising up to the top of the tree. And so once it's right below the answer stream, I would say we promote that. So before it was really just a successful state, but now that it's reached the top of the answer stream, it's promoted to become an answer. So at that point, nothing can come along and say that's not an answer. So the answer stream itself is, so it goes from a success to an answer. And with our conjunctions, so as I mentioned before, this goal is waiting on this tree portion to come back with the success. And so once that actually occurs, we'll take the state from that success, and then we'll apply to that goal so that we can evaluate the goal portion of our conjunctions. So this is kind of similar to that last one, but now that we just have a disjunction in the tree position. So all of the answers that come out of this search tree need to be evaluated in the context of that goal, or that goal needs to be evaluated in all the answers that come out of this tree portion. And so we'll take the success node, apply to the goal, that's this side, and then the remaining bit of the disjunction we'll also schedule over here on the other side of this junction. Finally, so we don't explicitly model failure in here, so whenever we fail, we kind of just want to prune it out of the tree. So with a disjunction, our left-hand side fails, we'll just keep the right-hand side, that can still succeed. But if the tree portion of our conjunction fails, that's an and, so the whole thing will fail. Right, so one of the nice things about doing this in PLT Redux is you get mechanization for free, but you also get synthesis for free. So we validate these, we synthesize a lot of these programs and just property-based test these things. So the first being syntactic preservation. So basically every reduction step performs well-formedness, where well-formedness is checking things like the substitution structure, the scoping of variables, relations exist and have proper arity. Next is determinism. So from a well-formed program, you can take at most one step. And so this would be nice in terms of the visualization. So we only take one step. We don't have to visualize any branching computations. And finally, this monotonic propagation of delays. So as we saw, the delays move up the tree. And this is basically saying you'll never have a case where the delay gets stuck somewhere down here. You'll never evaluate that tree. Right. So the visualizer itself. So this is like the high-level architecture of the visualizer. So the normal flow would be you load into the front end of the program, the API handles that, and then you start stepping through the visualization of your tree. And so as you step initially, you'll have a lot of cache misses. So what it'll do is it will go to the Redux model, so give me the next tree. That will be cached, sent back to the front end, visualize, good. But the reason we cache it is so, of course, you can step backwards. You could step forwards, backwards, and so there's a few changes I want to discuss. So the semantics I showed you are sort of a simplified version. The ones actually used for the visualization have some nice added features that make it, that lends itself better to the user experience and understanding what's going on. So these are actually changes to the model. These aren't things that we recover later on the JavaScript side. So the first being the railway model, second, basically relation expansion. So we'll look at those two in the slides. And these last three, we'll look at in the demo. So the railway model. So before, this is how we would do interleaving. Hopefully you remember, but we took S1 from the left-hand side, moved it to the right-hand side. But if you have a big S1 or a big S2, that's going to be a big swap. So I want to look at this tree. So this is not even a very big tree, of course, but as you can see, colored lines will point us down to where the evaluation is going to occur next. So we're looking at this subtree right here. That's a disjunction, point out a delay. So that's what we'll do interleaving. So we'll swap the ordering down here with the delay up. And then we do that again. We have another disjunction. We swap the order. And finally, as we get near the top of the tree, we swap the two entire subtrees. And so that jump right there is something we want to avoid because it's very disorienting, trying to keep track of what actually happened. So evaluation might continue further. We might hit another delay. So this is the conjunction, so we'll just move it up one. But then delay moves up, and finally we swap the whole tree again. So it's that behavior that we want to avoid. We don't want to have to have the user try to reacclimate themselves with this very different tree. So before we just had this one node for disjunction, and now up two. So second one is also a disjunction, but it's telling the evaluation context which way to go. So before we always evaluate the left-hand side. Now, depending on which disjunction node we have there, we evaluate either the left or the right-hand side. So interleaving with this new approach, so now we have two rules for interleaving, one for when we have a delay on the left, or when it's on the right. But if you'll notice, the relative ordering of the subtrees stays the same. So here, this is more like the old one, where we're looking on the left-hand side. After interleaving, S1 is still on the left, S2 is still on the right, the delay is still moved above the disjunction, but the disjunction itself is now saying go down the right-hand side. So the next time we come around, we'll still evaluate S2. That keeps them in the same order. And then for the right-hand side, it's something like a symmetric version. And so the other rules involving disjunction also need a second rule, or even in the case of the reassociating one, you have 4 rules there. So at the cost of more rules, though, you get a better interface. So what that might look like here. So again, looking down here at this subtree, at this time, whenever we do the interleaving, you'll notice the relative ordering of the trees stayed the same, but the arrow on the disjunction flipped. And so again, now we're looking here. We move the delay up, but the relative ordering stays the same. Finally, the big jump we saw earlier, much nicer, much cleaner, less things moving around. So evaluation will proceed, get another delay. Conjunction, we just move it up. And here, and swapping the order. Again, they stay in the same order, but the delay can still be enough. That's the railway model. Second, for lazy relation expansions. So before, on a counter relation call, we would do beta substitution immediately. That doesn't really make sense considering you just delayed that tree, so you're not going to evaluate it. So why would you expand your relation call and clutter up the search space? So as an example of that, we have this small tree here. We have 3 relation calls. So what we do before is we would expand the first one, we would expand the second one, expand the third one. And so that's disgusting. That's we don't need all that information in the tree, especially considering we're not evaluating it immediately. So this other approach, so we'll introduce this new wrapper go, so sort of like a thunk, but basically it's saying we're marking our relation calls as we've already seen it before, so you don't need to delay it again. But upon the first time seeing a relation call, we'll add the delay, we'll add the go, and then once the delay moves up the tree and gets erased, at that point, when we come back to a relation call, that's when we'll actually do our beta substitution. Right, so that looked like here, we would delay the first, mark it go, delay the second, mark it go, delay the third, mark it go. You can see state is very small, much more manageable. But also, there's a better correspondence between like what actually happened there, in the sense like this was a relation call that got delayed rather than whatever its body happened to be. So, demo. Right, so this is the tool itself. And so on the left-hand side here is where you would input your program at. And so the right-hand side contains the tree that you're visualizing. So I'll go ahead and load up the same example we saw from the introduction. And so hopefully this tree looks somewhat familiar to you. But as I mentioned, one of the UX improvements is we tag our goals. And what that gives us is some correspondence between the program itself and the search tree. And so say we clicked on this node here, this called the same with the fish as the argument. So that will highlight that goal within the program. We could also do that the other way around. So say you click this goal, which has dog in it, that'll highlight all occurrences from that goal in the search tree. And so that's nice, especially when you're deep in execution, to see some correspondence between what's happening in the execution and where it came from in your program. And so it works, so you can start stepping. And so, yeah, so we'll evaluate these goals basically. Sorry. So you can step backwards. So here we're trying to evaluate this call the same. And so that's a relation call. So we delay it. Again, we use lazy relation expansion here. So now it's green, it's marked ready to go, it's delayed. So what we'll do is do our interleaving. So we push the delay up the tree. As you see, there's a little right arrow saying go down the right-hand side next time. That will reach the top of the tree. We release it. And then that relation call also gets delayed, moved up the tree, interleaving, release. We go down. We had our cat relation call, delayed, move it up the tree. And then finally, we come back around to that. And so we can substitute this body in and do the evaluate the goal. And we actually get back the answer. So again, this is showing fish came out first, which was unintuitive at the start. But now that we have like this visualization, we can see exactly why that happened. Next, we look at turtle, evaluate that. We got our second answer, turtle. Finally, third one is just this raw unification. So that's not a relation call. We won't delay it. We'll just evaluate it. So that will become an answer. And then we got our last answer. So you can hover over the nodes to see the reified form of its substitution. So we get fish, turtle, dog, cat. Kind of pushing on time, so I'll skip past this. So the possible future work. So this is just one semantics for interleaving search, but there's a lot of scheduling decisions, a lot of interleaving strategies you might want to implement. And so you might want like kind of a pipeline for these sorts of things where you could construct your own semantics parameterized by parts of your scheduling strategy. And so once you have something like that, you might want to compare those semantics that you got out. So some comparative semantics, so showing some are equivalent, how they're different. Certain semantics have pathologies, other ones don't. And finally, mechanical verification. So proving some of these properties in Rock or Lean with our newfound knowledge of Lean could be nice. And so what you might end up with is sort of a unified framework for interleaving search where you can compare different strategies and visualization as well on top of all these things for those different strategies. Right, so to conclude this, we present this fine-grained deterministic small step semantics. So some models, mini-k-NERDS interleaving search, and then we use those semantics to power this visualization tool. So the source code is right here in the top, and then the visualization tool itself is hosted online, so you can access it there. Thank you.